and we'll start from the current slide. But before we get started, let me just mention this. I don't think it'll impact any of you, but just to let you know. I have a doctor's appointment tomorrow at 11:40, so I have to leave campus by 10:40. No, I have to be at the clinic by 10:40 for blood work, so I'm going to have to leave campus by 10 o'clock. Well, I'm normally in class in anyway, so I doubt if you'd be coming by. But just to let you know, I'm not going to be on campus at all from 10 o'clock until probably, I'm guessing around 12:30, 12:45, something like that, because my appointment starts at 11:40. Hopefully I'll be out of there by 12, and it takes about 40 minutes to get back to campus, so between 12:30 and 12:40. Again, I don't have any office hours there except 10 minutes in between my first and second class and 10 minutes in between my second and third class. So I won't have many office hours I'm missing. I'm just missing a whole class and the beginning of the next one, but that's for them, not for y'all. But just in case you were looking for me, I will be off campus from basically 10 o'clock until around 12:30, 12:45-ish, I hope. Okay, we already did example 3. Any questions on anything we've done so far? Okay, besides, when's our next first test? Okay, we'll try to move along on this as much as possible, as quickly as possible, if I can get this to do. Okay, example 4 is this. Discuss the existence of the limit as x approaches 0 of 1 over x squared. Okay? Now, just for a moment, let's glance back at this. The limit as the absolute value of x over x, okay, as x approaches 0. All right. I don't think I mentioned this before, but this to me is the key test for limits, and they barely touch on it, I think, in the book. I think in the old days, back the way we used to do it, this was something that I found very helpful. If x is approaching 0, what's the numerator approaching here? Absolute value of 0.
Always positive.
Huh?
It's always positive. But
well, yeah, but what's approaching is x approaching 0? 0. What's the denominator approaching? 0. Okay? Now that, in the old days, way back, you used to say, you can't divide by 0. And you can't. That's true. Okay? But 0 over 0, we used to say undefined, because anytime you saw 0 in the denominator, undefined. Okay? But when you have 0 in the numerator as well, that introduces a new possibility here, and that's called an indeterminate form. You can't tell if that's going to have a limit or not. Okay? And that's why we investigated. When we investigated, we saw that it doesn't have a limit. The absolute value of 0 is going to plus 1 from either positive or negative side, and x is going to 0, positive, negative, so it's plus 1 this way, minus 1 that way, this way, okay? And so that limit doesn't exist. But we had to investigate, all right? Now this form, 1 over 0, that is never, ever going to work. Never, okay? This is indeed an undefined form. So basically, in my mind, you look at that and say, not going to happen. Okay? There's no way. If it's 0 over 0, there's a possibility. It may or may not work. 1 over 0 is never, ever going to give you a limit. Okay? But they say, discuss the existence of the limit. We just did. It's not going to have one. Okay? Because that is an undefined form. 0 over 0, now we're no longer going to call it undefined, we're going to call it indeterminate. Okay? Negative 0.00000003 over 0 is undefined, okay? Because you can never divide by 0 unless the numerator is 0, and then you may have a limit. You still can't divide by 0, but you may have a limit. This one will not. Okay? Now, they do a graph of it. And one thing about the graph, this also is always positive, right? Whether 0 is positive or negative, that's 0. Can I get your name, please? Dakota, got it. I knew that. Okay. All right. Now, if you drew a graph of this, you know this as x is negative. Okay. I'm going to draw the graph. I was going to give it my blessing, but we don't do that. Okay. If x is negative and x is very large, that's approaching 0 way out here. But as it gets close to 0, it takes off, blows up. When x is positive, it comes in and does the same thing. Okay? Because this is a square here, no matter whether you put a positive or negative in here, the denominator is positive, the numerator is positive. That's what's happening. It's not got a limit anywhere. Okay? Now, some places and some portions of the book will say that has a limit at positive infinity. What is positive infinity? It doesn't exist. It's just out there, and it keeps going higher and higher and higher. There is no number for which that has an answer. You can start plugging in values for x, 0.1, 0.01, 0.001, 0.00001. That just keeps getting larger, larger, larger with no limit. Okay? I hope that's all we have to do. They draw the graph, and they talk about the what's happening as it approaches 0. Okay? And it goes really high, really fast. Okay, let's move to another kind. And I'll just erase all the ink on this slide, because this one's not on the slideshow either. Now, I mentioned to you, I think, before about the exercises in the back, or at the end of each section, and the odd numbers are all given at calcchat.com, and certain ones are at calcview.com. They go in more detail. Okay, those are free websites for the exercises. This author also has another free website. And I think this is the first one we've hit. This example 5, you can see larssoncalculus.com for an interactive version of this type of an example. So periodically you'll see that as well. So he has 3 websites. larssoncalculus.com, where he discusses and goes into more detail about some of the examples. calcchat.com for some of the homework exercises. calcview.com for selected ones of the homework exercises. Okay, so here's one of these that if you want more detail, maybe a better explanation than I'm going to give you, go for it. Okay, it says discuss the existence of the limit as x approaches 0 of sine of 1 over x. Okay? Now, sort of the same thing we said before. Take a look at where your variable is. What's the limit of that? X approaches 0. Where's 1 over x going?
0.
Say again?
0.
No, it's not going to 0. 1 over 0 is? 1 over 0 is? Undefined. Never happens. Can't happen. Okay? In fact, as it approaches 0 from the left-hand side, it goes extraordinarily negative. As it approaches 0 from the right-hand side, it goes way, way positive with no limit in sight. So how in the world can sine? What does sine do? That's what it does. It just oscillates between +1 and -1. As it goes negative for very large numbers, it's oscillating between +1 and -1. It goes positive for very large numbers, and these are very large numbers. As x approaches 0, it's just going up and down and up and down and up and down. This has no limit. There's no way it can have a limit. Number one, because the argument here has no limit, and the sign is just going to fluctuate between plus and -1. The graph is given in the text. Do all of you have a text now, or some of you don't yet? let me show you what this one looks like as best I can do, okay? We know the range of this is from plus or minus 1, okay? So this is going from -1 to +1. Never going to get outside of that, okay? You would think it would have to have a limit then, wouldn't you? It doesn't. Okay, and we'll put a +1 here and a -1 there, okay? And the sign of 1, if any of you check, what is the sign of 1 about? You got a calculator? I just thought you had it out there. Okay. Sign of 1 is about it's close to 0.5, but it's not, it's about 3/2, whatever that is. Some value, okay? Point seven something, okay? So that would be 0.7 something. That's up here. And somewhere about like there, and that would be negative down here because sine is odd function. Okay. Now, anything beyond 1, this gets to be a smaller and smaller number, right? 1/2, 1/3. So you're getting smaller and smaller, and you never. This is approaching 0, and between 1 and 0, sine is always positive, so this is just going downhill like that, and this one's going basically like that, okay? So what's it doing between -1 and 1? Well, you can start plugging some other things in here. When this is, say, 1/2, this would be sine of 2, okay? Now, sine of 2 is going to be, sorry, my string gets all wadded up. It's going to start, let's see, I guess it does somewhere down here reach -1, and then it starts going up here and getting close to +1, and then -1, and then +1, and then -1, +1, -1, +1, -1. Whereas on this side, it goes up here to a +1, and then it goes down to -1, and then it just goes going up and down, up and down, up and down, up and down, and they just get more frantic going plus or -1. But you see, as x gets closer to 0, from opposite directions, you can just go like this, faster and faster and faster and faster. There ain't going to be a limit there, anywhere. No way. Okay? That's pretty ugly, but that's basically what it looks like. If you got your books, you'll see a little bit pretty picture of it. Just not going to happen. Okay? If you only considered the, let's see, yeah, I won't go there. If you only considered the fractions of pi, then this is always going to be +1, -1, +1, -1. Just looking like that, you'd think it's there, but it goes every value in between. So I didn't think their table did a lot of good there, but they showed it. All right, any questions on those? If you see an undefined form, not indeterminate form, undefined form, hang it up. There's not going to be a limit. 1/x, anything where the numerator is not 0, denominator is going to 0, that's not going to have a limit. All right, so here's the summary, kind of common types of behavior associated with non-existence of a limit. Okay, 1, f of x approaches a different number from the right-hand side of c than it does from the left-hand side. If that happens, no way there's going to be a limit. We saw that in the example absolute value of x over x. F of x increases or decreases without bound as x approaches 0. In other words, undefined term, increases or decreasing without a bound. Or number 3, oscillates, f of x oscillates between two fixed values as x approaches c. It just oscillates faster and faster and faster. I can almost guarantee you this will have an undefined argument somewhere in it. Okay? Maybe not always, but quite often that'll be the case. Okay? Now, in your text, I don't know why, but he put this other function in here. And I did say it will almost always have a undefined argument. This one doesn't, okay? But here is a function, a real life function. F of x is equal to, now why they bring this up? This is a piecewise defined function, okay? Now piecewise defined functions, they're really going to be suspect, okay? Because unless these two functions, at the value where they have in common, unless they come together there and come together with the same slope, oh no, I'm sorry. As long as they come together, they will have a limit. But if they ever don't, then that's this case, okay? Now this piecewise defined function is a rather strange one, and it's a guy named Peter Gustav Dirichlet. Now I don't know how to pronounce his last name. He was German. Now that is a French-sounding last name if I've ever seen it. If that was French, it would be Dirichlet. But being German, it could be Dirichlet or something like that. I don't, Germanic and the Romance languages are from completely different backgrounds, so I don't know how to pronounce his last name, but I've seen this many times. Okay, here's his function. F of x is 0 if x is rational, and f of x is 1 if x is irrational. Where would you ever use anything like that? Well, possibly in a controller or something like this, but it's such a weird offshoot type thing. I don't know. This would be very hard to graph, okay? Okay. Because how many rational numbers are, say, between 0 and 1? Rational numbers between 0 and 1. An infinite number, okay? There's 0.1, 0.1, 0.001, 0.0001, and you haven't even gotten past 0.1 yet. Infinite number. How many irrational numbers are between 0 and 1? Infinite number, okay? There's the square root of 1 over the square root of 2, 1 over the square root of 3, 1 over the square root of 4, 1 over the square root of 5. All those are irrational numbers between 0 and 1. Infinite number there too. So what would this look like? You have a bunch of zeros here for the rational numbers and 1s here for the rational numbers. It looks like two solid lines, but it is a function because none of those really line up, okay? But you just can't tell because they're so close together. So it's a bizarre thing. They didn't even bother to do it. It's just sort of a offshoot example. I've never seen this in a Calculus 1 text. Someone mentioned Dirichlet's formula. I don't know how you pronounce his name. Now, they do have a little warning here, and they call it a technology pitfall. Okay? If you're using your graphing calculator, if you have a graphing calculator, and you try to do that sine 1 over x, it probably is going to look like it's going to have a limit. But that's because of how you define your inputs. And guess what? If you do your domain by just certain steps, you're skipping a lot of numbers. So this looks like it's a bizarre function, but sort of strange but regular as it gets close to 0. It's not. Between every one of these, there's an infinite number going up and down, up and down, up and down. It's just that some of them pan out there. So don't always count on your graphing calculator to give you a right answer on that. If you see that indeterminate form in there, write down does not exist. The limit does not exist. All right, now we're ready. Have you got your tuxes on? The formal definition of a limit, okay? And this is a little bit of a pain in the neck. Live through it. You can manage it. Let's take another look at the informal definition of a limit. As f of x becomes arbitrarily close to a single number L, that's the function, the y value goes close to some function L, as x approaches some value C from either side, then the limit as f of x approaches, the limit of f of x as x approaches C is L, okay? And that's what we get. This function is just a regular old function, and you can plug C into it, and you know that's the value, that's the limit, okay? If it's one of those indeterminate forms, and you manipulate it, and you find out you can get into a function, an equivalent function that has a limit, that's a limit. If it's one of those undefined functions, that limit doesn't exist, okay? First glance, that definition looks fairly technical, but even so, it is informal because the exact meanings, notice here, as f of x becomes arbitrarily close to. What do we mean by arbitrarily close to? As x approaches C. What do we mean by approaching C? Okay? You've got to get a little more meat to it than that. Okay? The exact meanings have not been given for arbitrary close to or x approaches. Okay? So let's see if we can come up with something a little better. First person to assign mathematically rigorous meanings to those two phrases was well after Newton, well after the German guy. Okay. Okay, scratch it. I'm going blank today. The other guy that came up with calculus at the same time, or at least claimed he did, was Augustin Louis Cauchy. I don't know if that's how you pronounce his name or not, but he came up with this definition called the epsilon delta definition of limit, and that's the standard that is still used today. In this figure, we give meanings to those arbitrarily close and approaches to, okay? So, here's how it states. Let epsilon, okay, that's just a little Greek letter E, epsilon, the lowercase Greek letter E, represent a small positive number. That's all you need. Let epsilon be greater than 0, small positive number. Then, when you're talking about alpha of x becoming arbitrarily close to L, that means alpha of x lies in between L minus epsilon and L plus epsilon. Remember, epsilon is always positive. So if your function is going to approach L, then it's going to be something in between L minus epsilon and L plus epsilon. Okay? Now, so you let epsilon be some small positive energy. Not energy, number. Okay? It can be a very tiny number if necessary. Okay? And then, as epsilon approaches 0, if you can always make this happen, then the alpha of x has got to go close to L. So for any epsilon you choose, you can make it close enough. Well, what does close enough mean? Well, C, remember, has to be, as x is approaching C, you introduce another value, and that's going to be your delta. That's where the epsilon delta comes from. So let's go to, and by the way, I don't know if you remember things like this. Remember, this is x and this is y, right? In the Greek alphabet, this is D and that's E, delta epsilon. So one letter off, okay? Lowercase, because it's a small number, okay? Using the absolute value, you can rewrite, I'm sorry, let's go back to this. Epsilon, the L is something in between L minus epsilon and L plus epsilon. So you can use absolute value and say L minus epsilon is, well, get there so you can see it. F of x minus L is less than epsilon. So this is saying your actual function value at any value x in L, if you get x close enough to that c, then this thing is going to be less than delta. That's the absolute value notation. F could be above it or below it, but as long as it's within that epsilon, you're fine. So similarly, the phrase is x approaches c, it's got to be between c minus delta. Again, you let there exists some positive number delta, small positive number delta, such that x lies on either side of c. C minus delta to c, or c plus delta, c to c plus delta. Remember, especially those indeterminate form, x can't equal c. It can't, because you're dividing by 0 again. But if you're in the indeterminate form, and it's somewhere in between c minus delta and c plus delta, getting closer and closer and closer to c, because delta is a small positive number, then you can say, again with absolute values, that x minus c is between 0 and delta, because delta is positive and this is 0. And up here, this is just less than epsilon. Almost the same type thing. It's also greater than 0, by the way, because it's absolute value. So you should put a 0 over here just like you did there, but they usually don't. Okay? So this is what they mean. Arbitrarily, F arbitrarily close to L, this is as x approaches c. Okay? That's how we define. Cauchy came up with that. So this first inequality, which actually to me was, the first is that 0 less than or equal to absolute value of x minus c. That's the distance between x and c. It's got to be more than 0, because remember, x cannot equal c, okay? Or usually it's not. We don't allow that. So as x gets closer and closer to c, it's still going to be positive because of absolute value, okay? And that emphasizes that x cannot equal c. The second side, the other half of that inequality, x minus c is less than delta, that means x is really close to c, okay? It's greater than 0, but really, really, really close to c, because it's less than that arbitrarily small delta. Okay, so x is within the distance delta of c. It can be on the left or the right, somewhere in between delta, x minus delta, and x plus delta. Okay, so here's that formal definition of a limit. Let f be a function defined on some open interval containing c. Remember, it's defined on something on the x-axis. C is somewhere in that open interval. Okay? Except possibly at c. It may be defined at c, but it doesn't have to be. But it's defined everywhere else on that open interval. Okay? Let L be some real number. Positive real number, negative real, some real number. Then the statement, the limit as x approaches c of f of x is equal to L, means that for every epsilon greater than 0, no matter how small you choose that epsilon, there is going to be some delta close to 0, but greater than 0, such that if x is within delta units of c, then guaranteed that f of x is going to be within epsilon units of L. That's the formal definition. So what you'll see how this works. And you sort of just have to slug through it for the first few times until you say, okay, got it, understand what it means, but let's move on. We'll come up with rules, and this is what Leibniz, that's who I couldn't think of, Newton and Leibniz did. They just went straight into taking derivatives. They didn't go through this formal definition. Okay? So here is example 6. Okay? Now, we can look at this and know absolutely, beyond the shadow of a doubt, this is true. The limit as x approaches 3 of 2x minus 5. What is that going to be? Well, first guess when you're doing a limit is just like the lathe. Plug it in, plug it in. Instead of approaches 3, just set it equal to 3 and see what you get. 2 times 3. 2 times 3. 6 minus 5. There's a limit. Okay. Now, we know that. We know beyond the shadow of a doubt that's going to be true. Let's prove it by the formal definition. Okay? Now, how we usually do this, you start with my calculus professor made us almost memorize this little, he almost made it sing-song. Let epsilon, and I don't draw epsilon as well as the book does, so I do it like that. Epsilon be greater than 0, okay? Then there is some delta greater than 0, such that, I like to abbreviate as much as possible with vertical lines, means such that for every time 0 less than or equal, I'm sorry, not equal to, less than x minus 3 for every value of x such that for some epsilon, you're targeting some epsilon, you're looking for the delta that's going to make this true. For every x, no matter how close to or far from 3, you have a delta such that this is true. See, x minus 3, this is x approaching 3, so that's what goes here. Okay, x minus 3, absolute value. X would be on the left-hand side or right-hand side of 3, but it's approaching 3. And for this number, of course it's going to be positive because of absolute value, greater than 0, but less than delta. That difference there. Okay? Then, let me go back and find my place here. Actually, they're not using the formal definition yet. Let's just take this, okay? We want to find a delta that when x is between that value of delta, that the absolute value, now here we put our f of x and our L. Absolute value of f of x minus L, okay, is less than this value epsilon. I probably should have said that first. Well, now this seems bizarre, but let's plug in what those things are. The absolute value of your f of x is 2x minus 5, okay, minus your L is 1, okay, and this is it Catherine?
Yes.
I'm sorry?
It's Catherine.
I can't hear.
She said yes.
Yes, oh, okay, I thought so, okay. I can't hear, okay. You do go by Catherine?
Uh-huh.
Okay, good, okay. And let me see. Is it Nolan? Yeah, no, oh no, Jordan. I'm sorry, I looked at the wrong name. Jordan, Nolan's already here. Yeah, Jordan. Got it. All right, anyone else come in while I was not watching? Okay. Okay, so here's what you have. Here's your absolute value of f of x minus L. We want it to be less than epsilon for this arbitrarily small epsilon you chose. So plug that in. Your f of x is 2x minus 5 minus 1. Okay? So that's going to be, we want this to be less than epsilon. Okay, well, what is absolute value of 2x minus 5 minus 1? First, combine like terms. 2x minus 6. Absolute value of that less than epsilon. Okay, well, I can factor out a 2, can't you? 2 times the absolute value of x minus 3. 2 is positive, so it can go outside the absolute value. Okay, and that's less than epsilon. Well, this absolute value of x minus 3 would have to be less. I keep wanting to put a equal, and it's not equal, just strictly less than. Divide both sides by 2, epsilon over 2. So there, we've done it. Okay, believe it or not, that's all there was to it. That is true because for any epsilon you choose, no matter how incredibly tiny it happens to be, you can come up with a delta, just take half of that delta, and you'll guarantee that for a delta less than that, you're going to have this less than the epsilon. That means for as small as you want that epsilon to be, you can get a delta that's going to make it work. That means the limit has to exist. Okay? Now, that seems like plugging in is so much easier, right? It's obvious that's the answer, but this is the formal proof of why that's true. You see, x never has to be equal to 3, but the limit is going to be that because no matter how close you get to 3, you're going to get that closer and closer and closer. Okay? It seems like a lot of work for something that's pretty obvious, right? But that's your formal definition. Okay? Now, let me erase my scratch, and you see if his explanation fills in anything here. Okay? Well, let's go back. Find a delta such that your absolute value of f of x minus L, that's the 2x minus 5 minus 1, is less than, now he chose I'm sorry. Oh, he didn't do that. He didn't actually do the formal definition. He started with, now this is not where you do a formal definition, but he said, let's let epsilon equal 0.01. That's pretty close to 0, right? Not there, but pretty close to it. Let's see if we can come up with a delta that always guarantees, no matter, that guarantees you'll be able to get within that. So we're going to do the same thing he did there. First thing you do is absolute value of 2x minus 6 less than 0.01 whenever that's going to be true. That's what you're trying to get for. You're trying to show this. So just like we did before, factor out the 2. X minus 3 less than 0.01, divide by 2, and now you know that the absolute value of x minus 3 has to be greater than 0, and the delta is going to be 0.005. Okay? Because when you divide 0.01 by 2, you get 0.005. Okay. If you want it within 0.01, choose a delta of that. If you want it between 0.0001, really close, add another 0 there. Just take half of whatever your epsilon is. In this problem, that's not work on all problems, that will give you your delta. Okay? Now there's some that will be a lot messier than that. So again, I interjected my chicken scratch. Let's just do his. Okay? So what in this problem, you're working with a given value of epsilon, 0.01. Okay, to find the appropriate delta, try to establish a connection between the absolute values, between the epsilon absolute value and between the delta absolute value. Okay? There's f of x minus 1 and the x minus 3. Whatever your limit though, there, x minus that limit. Okay? Well, that's what we do here. And just like we did, you separate that, and there you have what you got. 2 times absolute value of x minus 3 less than 0.01. You can choose delta to be half of 0.01 and get it 0.005. Now, again, it seemed like it would be easier if you wrote it out like we did, but that's how they do it. This choice works because anytime you choose an x that's close to 3, within that much of 3, okay, on either side, you're going to get your f of x within that much of one. It just, the math works. You don't have to deal with anything else on it. You know what it feels like to me, and maybe it does it to you, it feels like you're running around in a circle, okay? You're trying to make this work, so you choose something that makes it work. Yeah, that's okay. That's how they do these limits and proofs sometimes. They kind of feel circular. So here's what it means graphically. If you want, here's a function, f of x, 2x minus 5. The y-intercept is minus 5, the slope of 2. Okay? Let's focus on this part right here, around 3, as x is approaching 3. What's the limit of that? Well, we know what it is. You just plug it in and see. But as x approaching 3, what's your f of x? Okay? What is the f of x doing? It's approaching 1. Okay? And that's what we're trying to show. So if you choose a epsilon between 0.1, 0.099 to 1.01, something in between these two. If you choose a delta within 0.0005 of your 3, 2.995 up to 3.005, then this is going to guarantee you're going to fall between those. That means the limit exists. Okay? A lot of work to get something you can just plug in and see. Okay? But this is what guarantees it works. Okay? You do a few of these and then you say, okay, we'll believe that. Now let's do, oh man, they're not going to do it. Okay. Example 7 and 8, the harder ones, they skip on the slideshow. So let's do these. And oh, this first one, that's not bad either. Use the epsilon delta definition limit to prove that the limit as x approaches 2 of 3x minus 2, you tell me what the limit is. What do you expect the limit to be? Four. Plug it in, plug it in. 3 times 2, 6, minus 2, 4. Okay? And sure enough, that's what they say. Okay? So we're looking for, technically we say let epsilon be greater than 0. Then there exists a delta greater than 0 such that for any absolute value of f of x minus L less than epsilon, there must be a 0 less than, not equal to, x minus 2, okay, that's x minus c, that's what that is, less than delta. Okay, if you can find that delta in terms of those epsilon, you got it knocked. So start with this one, absolute value of, what you plug in for f of x? What's your f of x? What's your f of x? There's your f of x. 3x minus 2, right? That's your function. 3x minus 2 minus, what's your L? That's the 4, okay? Less than epsilon, okay? We want that to be the case. So let's play with this. What does that become? Absolute value of 3x. Do the math. Say again?
I say -6.
-6. less than epsilon. Well, can we factor anything out of that? 3. Absolute value of x minus 2. That's less than epsilon. Hey, look at that. That almost looks like this. The way to make it look like that, divide both sides by 3. I can't write. And there you found your delta. The delta must be epsilon over 3. Pick a small as you want it to be. 1/10 millionth. If you wanted that to be that, the epsilon of that, you can get a delta of 1/10 millionth divided by 3. And then that will guarantee you're going to be within those limits. So sure enough, that's how we do it. Okay? And then they plug it back in to show that you do get that. So it seems like running around your ear to get to your nose. I don't know. Now, again, a fairly easy one. Example 8, to me, is the kind that's sort of a pain in the neck. Okay? So easy to actually do, but the proof really stinks. Okay? And it's not bad, it's just messy. The limit as x approaches 2, I believe it is, isn't it? Of x squared is equal to 4. Oops, I should have asked you that. You didn't see that. Okay. What is the limit of that? 4. Okay. 2 squared is 4. Okay. Now again, let epsilon be greater than 0. There exists a delta greater than 0 such that whenever the absolute value of x squared minus 4, your f of x minus 4 minus your L, is less than epsilon, that 0 is less than x minus 2 less than delta. Okay. Now, I don't know if you followed from what we were doing before. You want to manipulate this to get it to look like that, right? Okay. What would be a good first manipulation here?
To square root, to get rid of the exponent, and to get rid of 4.
Okay, how's another way rather than taking a square root? That would be a messy square root, by the way. Okay. Now, I hope no one will get offended in this. I think Whitney is used to it. And maybe Dakota, I think maybe so. You know what I'm going to ask next? What's the F word? In my math class, what's the F word? Factor. Exactly. Okay. That's the F word. Let's try doing that. What does that give us? Say again? A little louder. What'd you say? X plus 2 times x minus 2. Now, why did I suggest that we factor? That's what we're looking for, an x minus 2. Well, here we have an x plus 2. Well, let's see. What can we do? So I left off a parenthesis, didn't I? Okay. Okay. Or a straight line 1, I can't tell. Okay. So, we need to do something about this x plus 2. Okay? You're interested at x is less than, close to 2, so the x minus 2 is what you're going to be interested in. And what you can also do is write this, absolute value of x plus 2 times the absolute value of x minus 2. That's also got to be less than epsilon. Okay, do you buy that? You just split the absolute values. Remember, this is always positive. These are always positive. Okay? This is positive and that. So this If you can guarantee this, you're the same as guaranteeing that. Okay? This is the one we want. We need to find some value here that'll work. And this is where the magic or the whatever occurs. You're interested in values close to 2, so choose an x in the interval, say from 1 to 3. That's pretty close to 2, right? Not super close, but somewhere. So choose the interval 1 to 3. I can't write. Okay. Choose x element of the interval, and that's not an epsilon, that's an element sign, 1 to 3. Okay? Somewhere in there. That's way bigger than you're going to need. So let's choose a value in there. Okay? Some x in between 1 and 3. Okay? Now, to satisfy that condition, for all x's in that interval 1 to 3, we want to look at what this x plus 2 is. Okay, that's this term here. Well, if x is 1, that goes from 1 plus 2 to 3 plus 2, right? If x is in there, okay? Well, this goes from 3 to 5, right? Your x plus 2 would be somewhere. For any x in between here, x plus 2 has got to be in here, right? 1 plus 2, 3 plus 2. It's got to be within there, okay? So let's choose the biggest one of those, 5, okay? So we are going to guarantee that absolute value of x plus 2 is less than 5, okay? We know it's got to be, we chose it that way. Anytime x is between 1 and 3. We're going to get much closer than that, so you're guaranteed to that. So, if that were the case, then if that's your epsilon, okay. That's as high as you can go. So if you did this one and plugged the 3, in there, that would be a 1. So then this would be, if this were less than 5, this has to be less than 1. So then this thing right here, this combination here, absolute value x plus 2 and x minus 2 would be less than epsilon. Remember, that's what we're starting from. Well, this is 5, and the x minus 2, absolute value of x minus 2 would then be less than epsilon over 5. Divide both sides by 5. Okay? So there's one value. Okay? So either x is, the absolute value of x minus 2 is going to be epsilon over 5. Okay? Or, let's go on the other side. If you chose your the lesser one, then it's going to be equal to 1. Let's see. Okay. So let's do the lesser one, the 1. We did the 3. If we did the lesser one here, it would be you wind up with epsilon equal to 1. So you're going to be the lesser of epsilon over 5, or 1. Okay? And then you're guaranteed that you're going to be within those limits. Again, it's just really messy. So much easier just to plug it in. I don't want to spend more time on that but you can read through it. This is one I wish he would have done using his Larson calculus. He didn't, unfortunately. But let's move on. 1.2 homework exercises. You can do any of the odds 5 through 9. All those are at calcchat.com. Number 5's at calcview.com. And all of you were here before, right? I told you this little, what you call this thing, the QR code? The QR code, you can just do it with your smartphone and it pulls it right up. You don't have to go to calcview.com at all. It pulls it straight up. Then do any of the odds 11 through 17. Do number 19. And by the way, all the odds are at calcchat.com. I won't say that every time. Then do any of the odds 21 to 27. They're all at calcchat. 23 is at calcview. Do 29 is at calcview and calcchat. Do 31, both at calcview and calcchat. Do 33, calcchat only. Then do either 35 or 37. Okay, you choose. Then do any of the odds 39 to 43. They're all at calcchat. 41's at calcview. Do any of the odds 45 to 55. All at calcchat. 47's at calcview. Do 59. Now that requires a graphing utility. It says be careful with those, though. They've already shown you that there can be some weird things going on there. And then try 61. You can think about 63 or 65. You don't have to do too much with those. 67, you can look at that as well. And 69 is estimating a limit, which is going a bit beyond what we've done in class so far. 71 is a good statement to look at. I think you can do that based on what we've done. 73 and 75 are true false. I assume they're still at calcchat. I haven't checked those out yet, but I assume they are. Think through those, see if you can understand why they're true or false. 77 is one that says you can think through that one too. 79, I think, is okay. 79 is one of those that it says using a graphing utility. If you're not careful with this, you can assume a wrong answer and it looks perfect on the graphing utility. So I'll let you play with that and see what happens. And then there's some proofs here. Are any of you pure math majors or most of you pre-engineering? Any of you math majors? Okay, if you're engineering majors, my guess is not that many engineering majors are going to really look at proofs that much. Okay, you're just wanting to get results. But you might want to look at these just to be able to train your mind and think through those. Now they have these things, I don't know if I mentioned it before, the Putnam Challenge. That's something that some type of competition they have, really tough exercises. Only look at those if you're interested. Okay, they are sort of fun, some of them, but don't get too bogged down with them. All right, let's move on. If there are no more questions here, any questions on 1.2? Let's move on to 1.3. Okay. All right. If limits ever can be fun, this is where they get to be a little more fun, in my mind. I don't want to poison your view of it, but all right. Evaluating limits analytically. And frankly, I've already shown you this a little bit. So let's move on. The objectives here, evaluate a limit using the properties of limits, and we'll go over those. We'll develop and use a strategy for finding limits. Okay? We'll evaluate a limit using the dividing out technique, which I think I've already shown you. Well, maybe not that one. Yeah, I think I did. Rationalizing technique, I know I showed you that one. And then evaluate a limit using the squeeze theorem, which to me then it gets to be a little more esoteric, and you have to be very careful and specific, and sure enough then you can prove some things that are a bit bizarre, but we can go on there. So let's first look at properties of limits. The limit of some function f of x as x approaches c does not depend on the value of f at x equals c. Now that seems rather strange, okay? It does not depend on that. And I think we saw some examples. If you have a function going along here, it has a hole here, and the value is actually down here, but then it goes along here again. And this could be a curve, it doesn't have to be a straight line, but it has a hole with a different value here. That's the value at f at c, but there's the limit is up there. Okay, so the limit does not depend on the actual value at x equals c. And that's why we say as x approaches c, not necessarily a value there. It may happen, however, that the limit is precisely f of c. And when that happens, we really like it. Okay? In such circumstances, such cases, we evaluate the limit by direct substitution. Plug it in, plug it in. Okay? And that's always the first thing to try. When you're looking for the limit as x approaches c of f of x, first thing I do, plug in c for x, see what you get. If you get an impossible situation, 1 over x, undefined, you know that limit doesn't exist. If you get a value, 12, 15/3, whatever, that's the limit. If you get something like 0 over 0, and we'll hit a few others, then those are indeterminate. Then you have to start scratching your head and doing other things. First thing you do, plug it in. That tells you which way to go from there. Such well-behaved functions, where as x approaches c, limit of f of x is equal to f of c, those are always continuous functions. Okay? Remember my description here? It's here, you have a hole, and then it continues here. With the values, that's not continuous. Because it's up here, there, you got it. Not continuous. Also, those piecewise defined functions, they come in at different things. Absolute value of x over x, different values. Those are not continuous functions. They will not always give you that value. Okay? If the point of discontinuity is you see. In fact, if that's the case, they're not going to be. So here are some basic limits. These are ones that we're going to take for granted, okay, or marble, or some other thing. If b and c are any real numbers, and n is any positive integer, okay, integer. B and c, any real numbers. Positive, negative, fractions, decimal, rational, irrational, it doesn't matter. Here's the first, and hopefully this is pretty obvious. The limit as x approaches c of b is b. Okay? What's the function f of x is equal to b? Describe that function for me. It has a special name. F of x equal b. Okay? What would be f? Okay, give me a value for b. Make up a number. Any number in the world. 5? Is that what you said?
Yes.
Okay, 5. So as x approaches 7, what is 5? No, as x approaches... Huh?
Okay.
The function is 5. You said it.
Right.
That's your b. Now what's the value of that as x approaches 7? What's the value of 5? 5, okay. If x approaches negative 4 million, what's the value of 5? 5, okay. So yeah, the value of some constant, no matter what x is approaching, that's a constant function. It's always 5, or negative 3, or 4/3, or whatever it happens to be. It's a constant function. No matter what x is approaching, it's a constant function. So that's going to be b, right? All right. That was easy, sort of, wasn't it? Now, how about this one? The limit as x approaches c of x. Say again? Someone said something.
I was saying, is it still x? Yes.
What's the limit? Is x approaching c? What's the limit of x?
C.
C! Okay, that's yes in Spanish, okay? Yes, it's c. Because this also has a name. That's called the identity function. If x is approaching c, then x is approaching c, isn't it? Okay? That's pretty obvious, okay? So that's going to be c. Now, for any positive integer n, the limit as x approaches c of x to the nth would be x is approaching c, so the limit would be, and by the way, this is called the power function. This is a constant function, identity function. These are your power functions. And you've seen them before. When n is 1, that's your identity function. When n is 2, it's your parabola, standard parabola. When it's 3, it's your cubic function. 4, it's your quartic function, looks a lot like a parabola. 5 looks a lot like a cubic function. You see those over and over again. As x approaches c, so nice, smooth, continuous functions, then this is just c to the n, right? Just plug in the c for n. That's what you get, okay? Now these two are pretty obvious. That may be a little more fuzzy, but it's still the same, okay? When n is equal to 1, these two are identical. And then for n is equal to anything else, they continue to be, okay? So those are your basic three basic limits, okay? Now, let's do a few of these. Yuck, I hate it when they do this. What's the limit as x approaches 2 of 3? 3, okay. You were, okay. What's the limit as x approaches -4? The limit of x? -4, gotta be, okay? I hate it when they give you the answer, okay? What's the limit as x approaches 2 of x squared? 4, obviously. 2 squared, which is, of course, 4, okay? Now, with those three basic ones in mind, let's look at some properties. Let me make sure I'm not skipping anything. Let's look again. Let b and c be any real numbers, n be any positive integer. Then, and let f and g be functions with these limits. The limit as x approaches c of f of x is going to be this L, and the limit as x approaches c of g of x is going to be k. Okay? Two limits. Okay? Now, here's the first property. And by the way, if you haven't run into properties like these first two before, you're going to run into them again and again and again and again as you do upper level math courses. These are what they're called the linearity functions, these two. Okay? Well, here's what we got. Scalar multiple. If the limit as find the limit as x approaches c of b times f of x. Well, we know what the limit of as x approaches c of f of x is. It's what? F. Okay? So, if you're just multiplying by b, the f of x by b, now, here is a shorthand way of saying that. The limit of a constant times a function is the constant times the limit of the function. The limit of a constant, and these are constants, okay, not variable. The limit of a constant times a function is the same as the limit, as the b times the limit of the function. Limit of the function L to the b by L. Okay? So there's your scalar multiple. You could have put, okay. Now the sum or difference. Okay? The limit of a sum or difference of two functions is the sum or the difference of their limits. Okay? And that kind of makes sense too, doesn't it? Basically it's saying you can, I wish they had put the middle steps in here. To me it would make it maybe go down a little better. To me the middle step here, let me get my pen set up. The middle step here would be that's equal to b times the limit as x approaches c of f of x. Okay? And then that takes you to that step, because we know that the limit as x approaches c of f of x is L, so that becomes L. Okay. So the limit of a constant times a function is the constant times the limit of the function. That's that one. Same thing here. The next step to me that makes sense is that the limit as x approaches c of f of x plus or minus the limit as x approaches c of g of x. Okay? And then that leads you to here. Okay? Because we know this is the rule that the limit of a sum or difference of two functions is the sum or difference of the limits of the two functions. You just interchange the addition or subtraction with the limit. Okay? And that's L. And that's K. Okay, so that's plus or minus L plus K. Now, sum or difference work? Do products work? Sure seems like they should. The limit of a product is the product of the limits. And to me, the intermediate step here would be that's the limit as x approaches c of f of x times the limit as x approaches c of g of x. So in other words, the limit of a product is the product of their limits. Same thing here, almost, that the limit of a quotient is the quotient of the limits, limit of f of x divided by the limit of g of x, with this one caveat. K can't be 0. That limit as x approaches c for g of x cannot be 0. Otherwise, this makes no sense. Okay? Well, of course, yeah. As x approaches c, if g is approaching 0, that doesn't make any sense. That's one of those undefined forms. And then, this is almost like the last one we had on the other, but slightly different. The limit of the power of a function is the power of the limit of the function. In other words, the limit of f of x divided by the limit as x approaches c of f of x raised to the nth power. So you can either take the limit of the function or take the function, take the power of the limit of the function, L to the n. Okay. Now with those in your tool belt, you can do lots and lots and lots of good things with limits. Let's do so. All right, here we go. What do you think the limit as x approaches 2 of 4x squared plus 3 is? Now you can do it the long drawn out way or you can do it a shortened way. I don't care. You tell me. Anyone? What would you do? Second? Second?
The short way.
Okay, and what would you do? What's your short way?
My short way may be a long way. I would just hit plug it in, the 2 and for the x.
That's exactly, to me, that's the short way. Okay, what does that give you? 19. Okay. Now here's what I think they wanted you to do. They wanted you to say that's the limit as x approaches 2 of 4x squared plus the limit as x approaches 2 of 3. And this would be the limit, 4 times the limit as x approaches 2 of x squared plus, what is the limit as x approaches 2 of 3? What's that limit right there? 3. Okay. All right. And this would be 4 times, I'll put it this way, the limit as x approaches 2 of x squared plus 3. And finally then, this is the limit, this is 4 times, what's the limit is x approaches 2 of x. Second?
16.
2, yeah, but that'd be 2, then square that, plus 3, and that'd be 4 times 4 plus 3. Why go through all that when you just plug it in and you do the same thing? Okay? But I think that's what they want to use those limit rules we just had to split a sum into the two limits of the sum, and then a product of the product times the limit, and then the power to be the limit times the power, and then do them all. You get all the same thing if you just plug it in. Please. Okay? Make sense? All right. Let's see how they did it. Let me erase all my scratch here. I like your short version first. Just plug it in. You get 19. Okay, let's see what they did. Oh, sure enough, they do. The limit is x approaching 2 of 4x squared plus the limit is x approaching 2 of 3. And that would be the limit of 4 times the limit of x squared is x approaches 2 plus the limit of 3 is x approaches 2. Okay? And then that would be, they did skip one step there. The limit of 2 squared plus 3, and that would be 19. Where you just plug it in, you'd been there a long time ago. Okay, right? So either way you want to do it. Okay, that's example 2. Any questions? All right. Oh, and here they draw a figure for you, okay? This limit is reinforced by the graph of f of x equal 4x squared plus 3. By the way, if you remember back when you were doing these things, this was the basic quadratic, y is equal f of x equal x squared, would be something like this. And then you add 3 to it, that's the vertical shift upward. And 4 is a vertical stretch, so that really stretches these things. And sure enough, if you plug in x equal 2, you get 4 times 2 squared is 4, 4 times 4 is 16 plus 3 is 19. Sure enough, that point is on there. That's what it's approaching from both directions. Okay. As if you had any doubt. All right. Oh, and now they get around to telling you this, okay? The limit is x approaches 2 of a polynomial function. Now, what is true about polynomial functions? Why can we just plug it in there? What's true about all polynomial functions? Does anyone remember? 2 characteristics of polynomial functions. Sort of like jazz. They're smooth. Always smooth. There's no points, there's no cuss, there's no other things. Always smooth and always continuous. Smooth and continuous function. And because they're continuous, you can just plug it in. So the limit of some polynomial function, like we just had, is plug in the 2 and you get, this one happened to have been that one. So plug in 2 squared. That's exactly what you did, the shortcut, right? That's right. Direct substitution property is valid for all polynomial functions and rational functions as long. What's the difference in a polynomial function and a rational function? What is a rational function? Does that mean?
Square root.
Second?
Square root.
No, those are radical functions. Okay, rational function. What's the first 5 letters of the term rational? Ratio. What's the ratio?
Fraction.
A fraction, exactly. So a polynomial function, you know what that is. It's a combination of sums or products of numbers and variables raised to positive integral values. Remember? If that was a 1/2 there, that's not a polynomial function. That's a radical function. If it was a 2.3, you can't do it. -2, you can't do it. Those are not polynomial. The exponents always of the variables have to be positive whole numbers. Okay, that's redundant. Okay, so that's a polynomial function. What a rational function is a ratio, numerator and denominator, both of which are polynomial functions. Okay, so you can do substitution in the rational functions too, as long as that denominator is never 0. You've done that before. Remember, you probably graphed those things back in an earlier life. Okay. So here's theorem 1.3. This is the middle of page 64. If P is a polynomial function, C is any real number, then the limit as P of X, as X approaches C, limit of P of X is P of C. Plug it in, plug it in. Any polynomial function do that. If R is a rational function given by R of X is P of X over Q of X, where both P and Q are polynomial functions, and C is a real number, as long as Q of C is not equal to 0. Because you can never divide by 0. This value can't be 0. So as long as Q of C is not 0, you can do this. Plug it in, plug it in. C in the numerator, C in the denominator. For the x's, do this out. And that's what it will always be for polynomial or rational functions. Okay. So I think we're ready for example 3. Here it is. What would you say this one is? What's the first thing to try? Okay, say again.
Is it 2?
I can't hear.
Is the answer 2?
2, let's see. That would be 1 squared. 1 plus 1. 2 plus 2 is 4 over 2 equal 2. Perfect. Okay? That's a rational function, both polynomial functions. Plug it in, plug it in. What would be the only place that you'd run into a problem there if x was equal to what?
0.
X0 will work fine.
-1.
-1, exactly. Then you can't do that. You can't plug it in there. Because if you do, you get a 1 in the denominator. And you'll get a numerator, not 0. I mean, you'll get a 0 in the denominator. But if you plug a -1 in up there, you get 1 minus 1. That'd be 0 plus 2. 2 over 0, never can do. That is an undefined form. Okay? So that would have no limit. Okay. That was all, folks. Okay. Let's see how they did it. Because the denominator is not 0 when x equals 1, you can apply the theorem, plugging it in, and that gives you 2. And they even drew the graph for you. Thank you very much. If you have a graphing calculator, you can do that. Otherwise, I wouldn't mess with it unless you just really get a kick out of doing that. Okay? Any questions? Okay, that's example 3. Let's move to, all right, more properties. Polynomial functions, rational functions are 2 of the 3 basic types of algebraic functions. Okay? What's the other one? It's the one you were mentioning. Radical functions. The next theorem deals with the limit of the third type of the algebraic functions, one that involves a radical. Okay, 1.4. Let n be a positive integer, okay? The limit below is valid for all c when n is odd. It's valid for positive c's when n is even, okay? It sounds like it's going to be pretty messy, but it's stuff you're used to. The limit as x approaches c of this nth root of x. Remember, n is some positive integral number, okay? Never going to be a fraction, a decimal, or negative, okay? It's always going to be a positive integer. So this is the nth root of x. The third root of x, the square root of x, the 17th root of x, something like that, okay? That's going to be plug it in, plug it in. But you have to keep in mind this only works if that n is even, meaning 2, 4, 6, 8, okay? The even root of a number requires that number to be positive. You cannot take the square root of a negative number. You can't take the 16th root of a negative number. You can't take any even root of a negative number. If that n is odd, though, yeah, you can take all of it. No problem. And if you want to go back to Appendix A, you can see actually the theorem, the proof of that theorem. Can't wait. Okay. All right. So, they jump right into 1.5. The next theorem greatly expands your ability to evaluate limits because it shows how to analyze the limit of a composite function. Now, what was a composite function? Remember what that was? One function composed with another, f of g of x. Okay? These are going to be really important in calculus. Probably in pre-calculus, if you had it, you thought, why are we doing this? It's just something else to throw at us. No, that's going to be pretty important here. If f and g are functions such that the limit as x approaches c of g of x is this value L, and the limit of f of x as x approaches L is f of L, well, yeah, that means that f is a continuous function. A polynomial function, a rational function, or a radical function if it covers all the same. Then the limit of x approaches c of f of g of x, you start with the x, put in a c, g of x is, g of c is L, and then the limit of f of L is f of L. Okay, so there you have it. That's a composite function. Okay? That's going to be really important. Probably next chapter, I think, is when we hit what they call the chain rule. Okay? Y'all ever heard of that before? Okay. That's where this is important. Okay? So let's find some limits here. And guess what we do if we need to? The first ditch effort is plug it in, plug it in. So what is the square root of?
The answer's 2, but I'm saying the square root of...
What'd you say?
I was saying the answer's going to be 2.
2. Okay, the answer is 2. The square root of 4 is 2. Now that's because this is a positive principal square root. If you're taking square root of both sides of an equation, you always have to do plus or minus. But if they just have a radical sign, you always assume it's positive. Okay, how about the next one? Two again. They like 2s, don't they? Because 3 squared is 9. 2 times 9 is 18. 18 minus 10 is 8. Cube root of 8 is 2. And that, again, is positive cube root. Well, it's the only cube root. Okay. The other 2 are irrational. I mean, complex. Okay. So let's erase what we did. And I think they'll show it in a little more detail. So if this is helpful for you, go for it. The limit as x approaches 0, just plug in a 0. 0 squared is 0, plus 4 is 4. Okay? Square root of 4 is definitely 2. Okay? On the b part, okay, you can conclude that. Yeah, I thought we just did. Okay? Let's do the b part. Plug in the 3. 3 squared is 9. 2 times 9 is 18. 18 minus 10 is 8. The cube root of 8 is 2. All right. And you can conclude that. Okay, good for that. All right. Let's move on to theorem 1.6. Okay, here are some limits of trigonometric functions. Okay? So we did our basic algebraic functions, polynomial functions, rational functions, and radical functions. Let's move to our trig functions. Okay? Let C be any real number in the domain of these trigonometric functions. Okay? Then the limit as x approaches C, and by the way, what is the domain of your sine function? All real numbers. Cosine function? All real numbers. The other 4 have limits to the domain. Remember what they were? the limit for your domains of your tangent function? What can tangent never be? Tangent of what is not defined? Your half pies. Remember, vertical asymptotes that pi has and minus pi has, and every half pi. So tangents are not defined at your half pi. Here's why. Because tangent is sine of a cosine, right? So anytime cosine is 0, tangent doesn't exist. When it's cosine 0, cosine starts at 1 and 0. Pi halves, 3 halves, pi, 5 halves, pi, 7. All your half pies. So that's why tangent is not defined in your half pies. How about cotangent? Where is it not defined? Cotangent is cosine over sine. So anywhere sine is 0. Where is sine 0? Need to talk with your trick teachers. Say again?
You said 0?
At 0. There we go on. Okay. Picture your unit circle here. Okay. Sine is
At 0?
okay at 0 at sine is y over r, right? 0 here, 0 here, 0 here, 0 here. Where are these? 0, pi, 2 pi, 3 pi, 4 pi, 5 pi, or minus pi, minus 2 pi, minus, whatever, That anytime. So on your whole pies, your cotangent function is not undefined at your whole pies. Pi, 7 pi, 14 pi, negative 3 pi, whatever, at the whole pies, not your half pies. Tangent is undefined. Secant? Any idea where secant is undefined? What is secant? Reciprocal function.
The opposite
Of what?
cosine.
Yes, it's the reciprocal of cosine. So anywhere cosine is 0, that's just like tangent. So anywhere tangent is undefined, secant is undefined. Because tangent is sine over cosine, secant is 1 over cosine. So anywhere cosine is 0. So these two are the same, your half pies, these two are the same, the whole pies. Okay? So that's what they mean by the domain. Okay? So sine and cosine, any real number will work. Okay? So let's see what the limits are. Boy, these are surprising, aren't they? Limit of is x approaches c of sine x is sine c. Limit of x approaches c of cosine x is cosine c. Limit of tangent x where x approaches c, as long as it's defined, is tangent c. Yeah, you just plug them in, I'm glad they put this big thing here. You could have just said plug in the value, see what you get. The only thing is now you have to check and make sure it's defined at those values for your upper 4. So let's do this one. I hate this. Okay. What's the limit as x approaches 0 of tan x? Is that?
0.
What you said? I couldn't hear.
0.
0, absolutely, because tangent of 0 is 0. Okay? Y'all are looking like, close your eyes, okay? What's that? Uh-oh. SpaghettiOs. What happens here? What you reckon? Say again? I still didn't hear. Yes, pi is cosine pi. What is cosine pi? Uh-oh. Where's your trick teacher? Okay. Okay. Cosine starts at 1. Pi halves at 0. And at pi it's negative 1. So that would then be negative pi. Perfect. Okay, there it is. You were reading that on the back. All right. Yeah, you just break them up. Remember, this is that product deal. Limit of this times the limit of that. The limit of a product is the product of the limits. This is pi, and that's negative 1. Okay? So that'd be negative pi. All right. Bet you there's another one. All right. How about this one? I'll read more. Okay. What you get? Zero, because sine of 0 is 0. 0 squared is 0. Yeah. This was the limit of a f squared would be the limit of f squared. That's sine x. The limit of sine x is 0. Is x approaches 0. So that's 0 squared is 0. All right. Oh, and by the way, I forgot to say this. This was a product of two functions. This was a composite of two functions. One was a squaring function, the other was a sine function, right? That's the composite function. So we just did that composite function thing. Okay. That's example 5. All right. A strategy for finding limits. Guess what our first step is always going to be? Plug it in, plug it in. Okay? I don't know if they'll quite phrase it that way, but let's try. You studied, of course you did, several types of functions whose limits can be evaluated by direct substitution. Name some of those. Polynomial functions. Rational functions. Radical functions. Trig functions. We just did those, okay? All right. This knowledge, together with the next theorem, can be used to develop a strategy for finding limits. Functions that agree on all but one point, okay? Let C be a real number, any real number in the world, and let f of x equal g of x for all x's not equal to C on this open interval containing C. So here's this open interval. The f of x and g of x are identically the same for all x not equal to C. Okay? If the limit of g of x as x approaches C exists, then the limit of f of x also exists. I've got to sneeze, I'm sorry. Thank you. Y'all awake yet? Okay. Now, poor people at home, they may not have realized that was done. Okay. So f and g are equal to each other, all values except possibly x equals c. We don't know about it there, but all other values it is. So they're the same functions except possibly x equals c. But the limit of g of x as x approaches c exists, so if g of x does, then the limit of f of x must also exist, because they're the same everywhere. So if they both have the same limits as they're coming down, then that will be the case. And that's what we've got there. Okay? They may not agree at x equals c, but the limits will agree. Okay? Now that seems like such a weird kind of thing, and maybe they'll show us an example. Here's one. Yes, of course. What you reckon you would do first to do that limit? Find the limit as x approaches 1 of x squared minus 1 over x minus 1.
Usually plug in 1.
Okay, and what,
and
what do you get in the numerator?
you get 0.
0. What do you get in the denominator?
0.
Okay? Can you say because you're divided by 0, it never has an answer? No, this is an indeterminate form. This is 0 over 0. Okay? He says 1. Okay? Let's see if he's right. Well, x over x or n over n is always 1 except for x or n is 0. We don't know that. So what would be your next best guess? See, everywhere else the limits would be the same, but we don't know what they are when x equals 0. This is fine, that's not fine. I mean, that's 0, but that's not. So, say again? Okay, I heard it undefined. It's definitely indeterminate because it's 0 over 0. If it was 1 over 0 or 15 over 0 or negative 3/10 over 0, that would be undefined. 0 over 0 is indeterminate. Now remember we said this I think I gave you an example like this before, but that was, I know, several days ago, and you didn't need to remember that, right? What might you do to that numerator? What's the F word? Factor it. Okay. Can you factor that numerator?
Yeah.
Different, two perfect cubes, what does that factor as?
Could you do x,
X.
then x squared,
Okay. Over here will be an x squared. I'll buy that so far.
and plus 1.
Actually, it's a minus 1. This becomes a plus x plus 1. Okay, there is a plus 1 in it. Okay, here's how I do sum or difference of two perfect cubes. Do the sum or difference of their cube roots. In other words, x, same sign, minus 1. Cube root of x cubed is x, cube root of 1 is 1, same sign. That's the first term always, okay, whether it's plus or minus. Then the next term, this factor, forget about this, square the first term, opposite the product here, square the last term. And that gives it to you every time. Okay? Now, if you do that over x minus 1, what happens? X minus 1's divide away. Okay? Now, what's the limit as x approaches 1 of x squared plus x plus 1? Say again? 3? Is that what you said? Not quite 1, right? Okay. So you can't do 0 over 0 equal 1. In this case, that indeterminate form produced 3. Okay? And the reason for that is these two functions, this function and this function agree everywhere except at x equal 1. Therefore, since this has a limit of 3 at x equal 1, the other one does too. Now, to me, the better way to say is analytically work with that, like factoring, dividing out, whatever. And they're going to come back and give that statement just a little bit later. Okay? In fact, they're going to do it right now. Well, close. Okay? Any questions for our races? And we'll see them do the same thing. Okay? Let f of x equal that. I far prefer it written that way than this way. This way, that dividing line is obscured. Okay? I would work with it like that. By factoring and dividing out the common factors, so that's where I would have left it in that first form. And that's exactly what we get. That gives you your g of x, as long as x is not equal to 1. Because x equal 1, f of x is not defined, but g of x still is, but that's the only place that they differ. And so the first function we had has a hole in the function. You can't evaluate this thing at x equal 1. It has a 0 in the denominator. But it's a indeterminate form, which means that with the proper selection of that, you can. When you factor out the x minus 1, you get that. So the only difference between those two functions is that is defined at x equal 1, this one's not. But otherwise the function is the same, so the limit is the same. Okay? Now, any questions on that? So we continue with our strategy for finding, oh wait. Oh, this is just continuing that same example. Okay. I thought we just did that. Didn't they do it here? We did it down there. Okay. Now they're just showing it in full and gory detail that those factor out the numerator, or factor the numerator. Notice you can factor out the common factors, divide them out, and leaving you with that, which is the g of x, and that gives you 3. Thought we just did that, but now we did it in gory detail. Okay? Now, here we get back to our strategy for finding limits. It says, learn to recognize which limits can be evaluated. Here's how you recognize it. Plug it in anyway. Okay? Substitute. Plug it in. If you get an answer that works, that's your answer. If you get an answer that doesn't work, evaluate why it doesn't work. Does it not work because it's undefined? If that's the case, throw it out. It doesn't have a limit. But if it doesn't work because it's indeterminate, 0 over 0, continue doing. Okay? So, when the limit of f of x approaches c cannot be evaluated by direct substitution, try to find some other function g that agrees with f except for that one value c. Okay? And do whatever it takes. The first technique is factor. Okay? And then they say use a graph or a table to reinforce your conclusion. Well, and right now they've only given us one tool, and that's the factoring tool. And now they're going to talk about it. Dividing out techniques. That's what we just did. Okay? One procedure for finding a limit analytically is for the dividing out technique, which we just used. It involves dividing out common factors. So in other words, you factor first and then divide. Now this example 7 coming up is another one that is at larsoncalculus.com. Okay? Interactive version of this type of example. Okay, what would you try first? Plugging it in. Okay? When you plug in a -3, what does this become?
Positive.
Okay, 9.
3. Negative 3.
Which would be?
6.
6 minus 6 is?
0.
0. Okay? That's going to be perfectly fine unless the denominator is also 0, which it is. Now, if that had been 7 over 0, undefined, hang it up, no limit. But this is 0 over 0. That's in indeterminate form. So therefore, keep plugging. What would be the next thing you would try? Factor that numerator if possible. Does that numerator factor? Now, I don't know what your techniques you use. I'm going to give you the one I like just because I like it. Okay? I unfoil it, right? You multiply two binomials by foiling. Let's unfoil it. Let's start with the first term. What's the only possible factorization of x squared? X times x. Okay? Then, I don't spell it too well. I look at the sign of the last term. What is that? Negative. What does that tell you about these two signs? Yes, they've got to be different. One positive, one negative. And then, since that's a negative, we want two numbers that multiply to be 6, of course, but whose difference, because they're different signs, is 1, plus 1. Positive 3 and negative 2. Okay, positive 3, negative 2. You probably did that in your head without having to go through all that. But if you wanted my technique, there's my technique. Okay, divide that by x plus 3, and lo and behold, what do you see happen? X plus 3 divides away. And that leaves you the limit as x approaches negative 3 of x minus 2. And what is that? Negative 5. So 0 over 0 isn't 1 anymore, is it? Okay, it is, in this case, a negative 5. Okay? Does that make sense? Okay? Let me erase my mess, and we'll see how they did it. Probably pretty similar. Although you're taking the limit of a rational function, you cannot apply the plug-in, they say, because the limit of the denominator is 0. Well, so what? Plug it in anyway and see that. You need to plug it in because if the numerator was 7 and the denominator is 0, right there, say stop. This does not have a limit. Okay, but if it's 0 over 0, then you proceed. So you still do plug it in, okay, which they did. And they show you direct substitution fails, but it fails only in the indeterminate form 0 over 0. If that had been negative 15 over 0, no solution, none whatsoever. No way you'll ever make it work. Factoring or anything else will not make it work. 0 over 0, that tells you to keep going. Indeterminate. You don't know where it's going. Okay, because the limit of the numerator is also 0, the limit of the denominator is, okay. So for all x not equal to negative 3, you can divide out the x plus 3. So you factor the numerator, and you see you can divide out x plus 3, and that gives you x plus 2. Then take the limit as x approaches negative 3 of x minus 2, and you get minus 5. Okay. I think we did all that a little bit shorter, though. Okay. Make sense? All right. And you can do the graph if you want to. You know you can't have a value x equal negative 3. That's not defined. Everywhere else, this is the line x minus 2. Right? Yeah. Y-intercept of negative 2 is close to 1. Yeah. Except you have a hole in the graph right there. Tells you that x plus 3. Make sense? I always do my graphs because I like drawing. No, I don't. You know, it's just fun to look at. Okay. So, in example 7, direct substitution produced meaningless form. I won't say meaningless. Here they finally tell you that. An expression such as 0 over 0 is called an indeterminate form because you cannot, from the form alone, determine the limit. You don't throw it out just because it has 0 in the denominator. That would be true if it was 7 pi over 0. Throw it out. Okay, that's never going to be an answer. Okay, but 0 over 0 is indeterminate. Don't throw it out yet. When you try to evaluate a limit and encounter that form, remember you must rewrite the fraction so that the new denominator does not have a 0 in the limit. One way to do this is divide out common factors. Now, that's one way. It's not the only way. Okay? They're beating this horse to death, aren't they? And they love these technology pitfalls, which is sort of good too. Because if you're using your graphing calculator, realize your graphing calculator isn't always going to get everything right. If you would have put that form that we just had in there in your graphing calculator, as long as you didn't define it for x equal negative 3, it's going to tell you that you have a nice straight line with every point in there. Okay, because it will connect the dots as long as that wasn't a dot. Okay. So, the next technique, and we've already done this one too, is the rationalizing technique. Another way to find the limit is the rationalizing technique, which involves rationalizing either the numerator or the denominator. Now, back when we were doing rationalizing of irrational fractions, we always tried to rationalize the denominator. Here, do whatever needs rationalizing. It may be the numerator or the denominator. We know that rationalizing the numerator or the denominator means multiplying the numerator and the denominator by the, remember the word, conjugate of the numerator or the denominator. Okay? So here we have a form, square root of x plus 4 over x. Okay? Now this is not one that would have a limit. Because the only place this limit would be a problem would be at x equals 0, right? But you can put x equals 0 in here and you get 4 over 0. That's not ever going to produce anything useful. So don't bother it with those kinds. But they're just showing you how to rationalize the numerator. How would you do it? No, I don't think I'm going to make it till 10:40 without a bathroom break. Do you mind if we take one? Okay. Because I've been talking a long time, and I know y'all are really excited to hear me talk. I don't want you sitting there uncomfortable. Well, I don't like being uncomfortable, so. Okay. So let's rationalize the numerator of this. Again, this has nothing to do with limits because you wouldn't even bother with this one if it was a limit because that doesn't have a limit. But how would we rationalize the numerator? What would you do?
Supposed to be multiplied by its conjugate.
And what would that be?
Square root of x
Minus 4, okay? But then the denominator too, square root of x minus 4. Got to do the same thing to the numerator and denominator. Why is this legal? Why can you multiply by this over that?
is equal to 1.
Equal to 1. You can multiply by 1 anytime you want to. It doesn't change the value at all. Okay? So what does the numerator become? What's square root of x times square root of x? X. Okay? And then your cross terms, the outer is minus 4 root x. The inner is plus 4 root x. What does that add to? 0. Okay? And then your last terms are negative 16. Okay? Over, and now it messed up your denominator. Okay? Usually we don't care, but it becomes x times the square root of x minus 4, which of course is just as messy as the first was. But if this form happened to be, and it's not, a case where it was indeterminate, doing that, it's probably not going to be indeterminate anymore. Okay? So you multiply the numerator and the denominator by the conjugate of root x plus 4, which is root x minus 4. Okay. And of course, when you boil it like this, you get a happy face. Okay, never mind. Okay. So let's do this limit. What's the first thing we're going to try? Plug it in, plug it in. What does that give you if you plug it in? The limit as x approaches 0 of the square root of 1 minus 1 over 0. And what's the square root of 1? 1 minus 1 is 0 over 0 is indeterminate. So now we do try some technique. If that had come up, negative 3 over 0, don't try anything. You're wasting your time. You'll never get that to work. Okay? So since that is indeterminate, we will try something else. Okay? I should have erased everything. Okay? What do you reckon the thing we're going to try now is? Multiply by its conjugate. Is that what I heard? Okay. And what is the conjugate of which? Numerator or denominator? Numerator. What's the conjugate of the numerator? The square root of x plus 1 plus 1. Okay. Over the square root of x plus 1 plus 1. Okay. Now, admittedly, that's going to mess up your denominator big time. And if you're doing irrational, if you're trying to divide this, you don't want radicals in the denominator. You were happier with the way it was before. But that's not what we're doing. We're trying to find limits now. So let's see what that numerator becomes. You tell me. X plus 1 is the first term. It's actually two terms. And what's the next part? Minus 1. Okay. There's your numerator, denominator. Just leave it like it is. X times the square root of x plus 1 plus 1. Okay. Now, what's that numerator become?
X times square root of x plus 1.
Okay, the numerator is just x, isn't it? Okay, because plus 1 minus 1 is 0. Okay, and the denominator is just this. So that's going to be x times the square root of x plus 1 plus 1. Okay, now what would you do with that one? What do you do with Glade? and x equals 0, that makes the numerator 0. Uh-oh. But look at what the denominator becomes. Oh. Wait a minute here. I haven't done something wrong, have I? Oh, yeah, stupid me. Don't plug it in yet. Why did we do this? So we can factor out the x's. So this becomes the limit of, as x approaches 0, of 1 over the square root of x plus 1. I made that way too long. Plus 1. Okay? And what does that give us? Numerator is? Pretty obvious, isn't it? One. Okay, and the denominator is square root of 1, which is 1, plus 1 is 2. So 1/2 is your limit. Okay? Don't go through all that work and then fail to see that that's what divides out for. Okay, so that limit is 1/2. Good deal. All right. Let's see how they do it. I bet you it's about the same way. Any questions for our races? Everybody got it? Okay. By direct substitution, you obtain the indeterminate form. So go on and do your direct substitution, okay? You get that form, then decide what to do next. And here we will, well, they should show how you get 0 over 0. Direct substitution fails. So now multiply numerator and denominator by the conjugate of the numerator, which is square root of x plus 1, plus 1. And when you do that, you get exactly what we did. And that gives you x over x times the square root of x plus 1, or the x's over x divides out to 1. And that gives you 1 over that as long as x is not equal to 0. Remember, that's what it couldn't be before. But now take the limit of that. It's just a different form. You see, what they've done is the first one, and they use this other function right here in the second one. And when you do that limit, you get 1 over 2. So that limit is indeed 1/2. Just not define that x equals 0, but it has a limit of 1/2 when x is equal to 0. Okay, and here is their graph of it. Now, this is a weird looking graph. And I can't really tell you much that makes it make any more sense.
Here, back to basics. Why is the star at negative 1, and then why is there a hole in graph?
Yeah, the hole in the graph of x equals 0 because it's not defined there. But when you get that other form we just had, let me go back and show you. That form is just not obvious why that turns out the way it does, but it does. Just plug it into a graphing utility and you'll get a form that looks like this. It may not have the hole in the graph. You have to put the hole in the graph there because you know that's not defined as x equals 0. Okay. The limit, though, is 1/2. It's approaching 1/2 from the left and from the right, so therefore that is the limit.
Just not defined at 0.
Okay, is that what you were saying? Okay. My hearing's bad, so I can't tell. What's that? That's what I was saying. This is not one that I can explain using, what do you call those things?
I see how it went up.
Transforms, huh?
I see how it went up.
Okay. Yeah.
You talking about like how it curves up?
Okay.
Where the left one and because that negative, plug in -1, f of x equals 1.
Right. Yeah. You can. That's what I was going to say. Just plug it in, use a graphing utility, and get the graph like this. But I think what you're asking from your transformations. Oh, transformations work okay when you're multiplying or dividing by numbers, multiplying and dividing by variables. That makes for a lot messier situation. Okay. And I tried to. I thought if we looked at the other side, that's even worse. So you just have to either, like you say, do a t-table and plug in values, and you see how this is going to go, or use graphing utility and you see how it's going to go. But I can't tell you, oh, well, sort of like you said, you can see where it has a horizontal shift to the left 1. That kind of makes sense. But then the rest of it, especially dividing by x, that it just it's somewhat bizarre. There's no reason to look at this and think you're going to invert that, because you're not. If this was a minus here and a plus there, that would make perfect sense this way. Okay? But it's not. It's a plus here and a minus there, and that's why I said I can't really. And then dividing by x is just, you just have to graph it. That's it. There's no, what do you call these? Transformations of functions, adding, stretching, shrinking, that kind of stuff, and shifting. That's not going to do it for you. It'll give you a little bit, but it won't give you the whole picture. Okay. All right. And this is showing from the table. If you approach 0 from the left and the right, and they just choose some x values that are fairly close to 0, but not there, 0.25, negative 0.25, negative 0.1, 0.01, 0.001, and this is getting closer and closer to 0.5 here, and positive 0.25, 0.1, 0.01, 0.001, plugging those in to that other form gets you closer and closer to 0.5. So sure enough, that limit is 0.5. Okay. This is so tedious to do, but if you need to do it just to convince yourself, that's fine. Okay. Now we move to the squeeze theorem. And there are applications of this which you really will need to think through those issues. But most of the time this is only it takes very special circumstances for this to work. And here's what it is. The next theorem concerns the limit of a function that is squeezed between two other functions, each of which has the same limit at a given x value. So there's a lot of conditions. The first condition is g of x is always greater than h of x. Always. And alpha of x is always in between those two. So what you have here is h of x less than or equal to alpha of x less than or equal to g of x for all values within this interval. Okay? That's the first thing. That's sometimes tough to find functions that will be the case. But the other thing is that h of x and g of x have to have the same value at the c that you're evaluating the f at. So again, it's a little bit of a bizarre situation. H of x always less than or equal to alpha of x, always less than or equal to g of x, and the h of x and g of x happen to have the same value at the place where you're trying to evaluate alpha of x, that you don't know what alpha of x is. Or same limits anyway, maybe not the same values. Okay, so that's a lot to match up. But when you get it to match up, yeah, squeeze theorem is very powerful. So here's how we state it. If h of x is always less than or equal to alpha of x, and that's always less than or equal to g of x, for all x's on some open interval containing that value c that you're evaluating, except possibly at c itself, because it may not have a value there. And the limit of h of x as x approaches c has to be the same as the limit of g of x as x approaches c, So you see if those limits are the same, that means as x is going to c, these things are going to the same value. These alpha has to be at that same value too, if that. Then the limit is x approaches c of alpha of x also exists and is equal to that same value of those. So the squeeze theorem is also called the sandwich theorem if you're hungry, you know, I'm sorry, and or the pinching theorem if you're mean. No, something else. So here are two special trigonometric limits that actually use the squeeze theorem. Okay? Now, here's the first. The limit as x approaches 0 of sine x over x. Okay? First, what would you do if you were going to do that? It didn't tell you what it was. What would be the first thing you would do? Plug it in, plug it in. What is sine of 0?
I was going to say it was going to be undetermined.
Yeah, and it will be indeterminate. Absolutely. Now, there are no factoring techniques or rationalizing techniques that are going to work to solve this one. Okay? However, I am going to suggest something to you. The answer is 1, and they're going to show this using the squeeze technique, but I'm going to suggest something else too. Picture what the sine function looks like near 0. Any idea? Let's say at pi halves, sine is 1. Okay, at minus pi halves, it's negative 1. Okay, and it's following through something like that, right? That's sort of how the sine function looks. Everybody agree? I mean, my drawing stinks, but that's generally how it looks, right? 0 at 0. Now, I want you to mentally picture this. How about that denominator? That's the identity function. That's x equal y is equal to x. Look at those. They almost line up on top of each other as you're close to 0. And as you're close to 0, it's the same thing over the same thing. This time, that is 1. Okay? Now, they're going to do it with the squeeze theorem, but I'm thinking, let's look at this and see what happens. They look like the same functions in there close. Close. You don't when it gets curving out here or up there, but close, that's almost linear. And itself over itself, there, in that case, that is equal to 1. Now, if you were to plug in this one, the limit of 1 minus cosine x over x, what is cosine x as x approaches 1? X approaches 0. Cosine is 0. 1 minus cosine is, but cosine starts at 1, right? So this is 1. 1 minus 1 is 0 over 0. So sure enough, that's 0 over 0. But that 0 over 0 is not the same as this 0 over 0, is it? So let's also maybe do a little bit on that one. What does that look like? Okay. Well, the cosine function basically is like that, right? Near 0. And 1 minus the cosine function would be something like that, wouldn't it? Well, no, not that. No, yeah, that would be it. Sorry about that. Okay. And then over x, that would be something like that. Well, guess what? This function, as you get closer and closer to 0, that's closer to 0. That's varying greatly. So sure enough, this wins. And that's going to take it down to 0. Now that's not as, to me, as good an argument as that one is, but indeed, that's what we got. So let's take a look and see how they do this. Find the limit. Oh, huh. I thought they were going to use the squeeze theorem to show that. They didn't. Oh, they do give some proof in the book And this is a pretty nice proof. Now, this is not this. We've already gone past this, but I'm going to use the screen here. For those who don't have a book, they do a triangle and a unit circle, okay? And they label several points here and do the areas of these things, and they come out with the squeeze theorem. They use the squeeze theorem here to prove this. And the cosine theta less than or equal to sine theta over theta less than or equal to 1. That's 1 at 0. That's 1 at 0. So this is 1 at 0. There's the squeeze theorem applied right there. And a pretty nifty case for it, too. So I'll let you take a look at that. And now, by the way, remember when I was telling you about Screencast-O-Matic, it only records what I say and what's projected on the board. My book and my arm waving, that doesn't get caught, okay? So when you're home, you don't see all that. People at home only saw this screen and me talking, okay, with nothing to make it make sense. Let's do example 9, which is indeed this one. Find the limit as x approaches 0 of tangent x over x. What would you do first? Plug it in. And what does that give us? What does that give us?
Indeterminate.
Second?
Indeterminate.
Indeterminate. Yeah, it's 0 over 0. Tangent of x, 0 is 0, x, 0 is 0. So that's the indeterminate form. So what might we try next? We have two things that we've talked about. Factoring and... Okay, let's try factoring. How does tangent factor? Oh, I got to talk with your trig teachers, okay? I've already said it today once. What is tangent? Sine over cosine. That's sine x over cosine x times 1 over x, right? Just had to do something with it. Right? Now, can you think of anything else to do with that? Okay. I'm going to go back a slide. Right here. Let's get that sine x over x. So what that means is let's rearrange this to be sine x over x times 1 over cosine x. That's legal in most states, isn't it? Right? This is a product. What's the limit of this as x approaches 0? Oh, I'll soon forget. What is it? 1. Okay, so that's 1. And what's cosine x when x is approaching 0? Who are your trig teachers? Okay. What's cosine x as x approaches 0? It's cosine of 0. Second?
No, I'm saying oh. I said oh. Yeah.
Huh?
Nothing.
Don't
I'm
know?
saying oh, like.
Yeah. Okay, cosine of 0.
1.
1! So this is 1 times 1 over 1, which is 1. So this answer is 1. And I don't know if this helps or not, but if you picture the graph of a tangent function at pi halves or minus pi halves, tangent is undefined, and at positive pi halves, tangent is undefined. Okay, because of that thing. At 0, tangent is 0, and at pi quarters, does anyone remember what tangent is there? Pi quarters is 45 degrees. That's 1. And down here it's minus 1, right? So a tangent function does something like this, right? And if you look at that and look at the x, again, those two lines are almost the same. One over the other is going to be 1. Now that's not proving anything, but graphically, doesn't that make you feel warm and fuzzy inside? Yeah, this looks like this could be 1. And indeed it is. Okay? Can I go on and erase that? Yay or nay? Okay. Really responsive bunch this morning. Okay, how are we going to do this? Let's see how they do it. I bet you they factor first. Direct substitution yields the indeterminate form 0 over 0. So that means you investigate further. And by doing this, we can rewrite tangent as sine over cosine. Okay? And then, and 1 over x is 1 over x, but then flip the cosine into x, because they're both in the denominator. And this gives you a form you know. And this is a form you know, and it just happens to be both of those factors of that product would be 1. Okay? Because the limit as x approaches 0 of sine x over x is 1. And the limit as x approaches 0 of 1 over cosine x is 1. So therefore the product would be 1. Boy, takes a while for them to get there, doesn't it? All right. Now they do show, weirdly, let's see if they show the graph of that. I never would have guessed it looks like this, but that's what it looks like. And it's not too surprising. When you remember my graph that I did was like this, and you divide by this, well, that divided by that is 1, and that's almost 1, that ratio. They're almost on top of each other for quite a while here. And then this is negative and x is negative, so that puts that up to be positive. And this is positive and that's positive. So that throws it up to be positive. So that almost looks like an even power function, doesn't it? It's not, but it almost looks like x to the 6th or something like that. Here's why it's not, because this is spreading outward, the others usually going up much more sharply. So that's the limit of f of x as x approaches 0 is indeed 1. Okay. That's the last example they show. Let's do example 10. And we've got to sort of hurry to get this one in. Find the limit as x approaches 0 of sine of 4x over x. Okay, when you plug it in, it becomes indeterminate. So we've got to figure out something else to do. But unfortunately, that's not the same thing as we had before, is it? Okay? We know what sine x over x is, but we don't know what sine of 4x over x is. Yes? All right, I think I heard you say multiply numerator and denominator by 4. Is that what I heard? Okay, you'll let me get away with it, okay? And it's only because we're running out of time. But isn't that true? Multiply numerator and denominator by 4. Okay? Now, without this in the picture, what is that? Sine 4x over 4x. That's 1. Right? Just like that is. Let's let u equal 4x, right? That'd be sine u over u. That would be 1. And 4 times 1 is 4. So that answer is 4. Okay? I sort of rushed that one through because we were running out of time. But sure enough, that's what we got. Okay? And then they did say there's a technology blurb at the bottom. This one's not warning you of errors in it, but it says you can use your graphing calculators to do other stuff. Let me give you homework exercises in 1.3. And remember, all the odds are at calcchat.com. So do any of the odds 5 through 21. They're all at calcchat.com. 7's at calcview.com. Then do either 23 or 25. They're both at calcchat. 25's at calcview. Do any of the odds 27 to 35. They're all at calcchat. 29's at calcview. Do either 37 or 39. They're both at calcchat. 39's at calcview. Do any of the odds 41 to 45. They're all at calcchat. 43's at calcview. Do any of the odds 47 to 61 on the next page. And these are all odds are at calcchat.com, but 53's at calcview.com. Do any of the odds 63 to 73. They're all at calcchat. 65's at calcview. Do any of the odds 75 to 81. They're all at calcchat. 75's at calcview. And do any of the odds 83 to 89. They're all at calcchat. 83's at calcview. And then there's a squeeze value, squeeze theorem problem at 91. So try that if you'd like. And also 2 more at 93 and 95. So try those if you'd like. Excuse me. There's an exploring a concept thing at 97. I don't know if those are at CalcChat or not. You might want to look at that to see. There's a writing one that you don't really have to write, but think through 99. And I'd say pretty much the same thing for 101. That's using a position function that you probably, if you've had physics, will recognize from physics. Otherwise, you probably will be taking physics at some point, so get used to it. So 101 would be a good problem to look at. And then using that concept, you can do any of the odds. No, do 103. I'm sorry, I thought there was more than that. Just 103. And then there's a finding a function, 105, and then proofs 107 through 111. You could do any of those you'd like, but don't get too bogged down with them. 113 is sort of something to think through. 115 through 119, the odds 115 and 119 are true false, and you, sorry, can't breathe. I think those are at CalcChat as well. There's another proof at 121, graphical reasoning at 123. It's a little bit more involved problem. You can take a look at them if you choose. I think that's the end. And we will start next time at 1.4. Any questions? Okay, good deal. Where did we start today? At 1.2? I think we were. So we did 1.2 to 1.4. Good deal, folks. Oh, and the question earlier was, when are we going to have our first test? We're going to do 1.4. We're going to do some in 1.5, not a lot. So the first test will probably, I'll have ready for you on Wednesday. Okay? Is that going to meet Whitney's timeline? And weren't you and Whitney concerned about that? Huh? Yeah, the first test. I'm going to try to have it ready for you on Wednesday. Okay?